right, so picking up from last time, we had just derived the equation for electron current. Now let's do an example. So suppose I is equal to 7.5 times 10 to the 18 electrons per second, and these are drifting through a copper wire with a diameter of 3 millimeters and a density of mobile electrons of 8.4 times 10 to the 28, 1 over meters cubed. I would never expect you to know those values for different metals. All right, so what is the drift speed of the electrons? Okay, so area is equal to pi 3 times 10 to the minus 3 meters over 2 squared, which is 7.07 times 10 to the minus 6 meters squared. Expect to see small areas because wires are not very big. Okay, so we'll hold on to that value. And now we can go after V bar. So V bar is equal to I over NA. So we'll plug in our current rate, which was 7.5 times 10 to the 18 electrons per second, over N, which is given in the problem, 8.4 times 10 to the 28, 1 over meters cubed, times 7.07 times 10 to the minus 6 meters squared. And our drift speed is 1.26 times 10 to the minus 5 meters per second. So pretty straightforward. All right, let's do a little bit more with this setup. And we're going to find something interesting that we will dissect in the next chapter. So how many minutes would it take for an electron traveling at this speed to go 90 centimeters, or about 3 feet of wire? So T is equal to distance divided by speed is equal to 0.9 meters divided by 1.26 times 10 to the minus 5 meters per second. And so we get T is equal to 71,428 seconds, which is equal to 1,190 minutes, which is equal to 19 hours. Does it take 19 hours for a light to turn on? Very, very interesting. So we will come back to this in chapter 18 and find out the mystery of the slow electrons. All right, so let me introduce a concept called conventional current. We have Benjamin Franklin to thank for this one. So we know current consists of drifting electrons. There are a few materials in which current is positive or appears to be positive, where current behaves like a positive. Are moving. This is called whole current. It is the exception, not the rule. So we call this whole current. But we now know with the discovery of the electron that it is the negative charges that are moving, not the positive charges. Now, we did not discover the electron until almost the 1900s, but we have known about circuits far longer. So let's see if it would have made a difference in terms of observing circuits, whether or not it was positive or negative charges going. So Electron current moves from the negative end of a battery to the positive end. And this is because it will move opposite to the field. So if you've got your field going this way, then your electrons, which have a negative charge, will move the other way. And then if you have your positive charges, they will move this way. So what we see now is that it doesn't matter, because these two negative signs, the negative charge going the opposite direction, ends up giving us the same value as a positive charge going the direction of the electric field. So, and you can tell whether or not you're dealing with electron current or hole current, but this is a new discovery, and it definitely comes after the work that was done to derive these current equations. So hole current goes the opposite direction. And if we use Biot-Savart, we can see that it actually doesn't matter which charges we think are moving, because you would have plus E going plus V bar is basically the same as minus E going minus V bar. So it actually, the equations work out, even though Benjamin Franklin made the wrong assumption. So this brings us to conventional current, which basically assumes the positive charges are moving. This is what we still use to understand current today. We denote it with a capital I. And it describes the amount of charge passing through a point in a second. All right, so let me write out the formulation for conventional current. Conventional current, capital I is equal to Q NA V bar, and the units are coulombs per second or amperes. So 1 coulomb per second is equal to 1 amp. And the direction is opposite of electron current. So, and one thing to note, in a metal, Q is equal to E, but in an ionic solution, Q could be a multiple of E. All right, so let's relate electric field to current. So V bar is equal to UE. U is electron mobility. E is the electric field. And so you can write I is equal to Q, NA V bar is equal to Q, NA U E.